got some questions how to solve them, or what would be the correct solution. In particular, there was one example, or there was one quiz question for perturbed gradient descent. So if I remember correctly, please correct me if the question was different than what I have remembered. So you had given a convex function. So this f here, f is a convex function of some parameter vectors, for example, w. And we assume it is smooth, so it has, we can compute the gradient. The gradient is well defined for each point, and it is also strongly convex. So this is to make sure that there exists an optimal vector such that f w star is the minimum. So there's a minimizer. And yes, sorry if some of you are now in the lecture hall. I tried to announce it by Slack today. So today I'm in Zoom only, but you can of course follow me in Zoom also in the lecture hall. So the lecture hall is reserved. You can stay there. Sorry for the misunderstanding. Okay, so we have the existence of a minimizer. And the question was, is it possible to find a choice for the step size or for the learning rate? So here we have the learning rate alpha k, which is required to be between 0 and 1, by the way, but otherwise arbitrary. So can we find a choice for the step size such that this iterates, so that wk eventually converges towards the optimum? And the answer is no, because by an proof by contradiction argument, so let's assume there would be such a sequence. So we would find a sequence such that the iterates get closer and closer to the optimal weight vector. So what would that mean for the gradient? So let's assume we have a sequence. Or let's assume we have found alpha k step sizes that satisfy this constraint. So they are between 0 and 1, and wk converges to the optimum. So what does that mean for the gradient? How does the gradient behave? What can we say about the sequence of gradients? So for each iterate, we compute the gradient. So we get a sequence of these gradients. What can we say about the gradients? Yes, it must tend to 0, because this must go to the 0 vector, because the gradient at the optimum is the 0 vector for a convex function, and it is, I assumed it's also a smooth function. So the gradient cannot increase arbitrarily if you stay within a certain neighborhood of the optimum. So if we get closer and closer to the optimum, also the gradient must get closer and closer to the 0 gradient for the optimum. Okay, but if we then look at the update at the perturbed gradient descent step, so what we get is minus alpha k, and this gradient here gets smaller and smaller. So this one eventually becomes negligible because alpha k cannot be larger than 1. So we cannot amplify this ever more decreasing gradient, or this gradient that goes towards the 0 vector. We cannot amplify it arbitrarily large because alpha k is required to be between 0 and 1. So this one becomes 0. So what remains then is this perturbation term, ek. So what we get is that for sufficiently large iterations, or sufficiently high iteration numbers, this difference between consecutive perturbed gradient descent steps is approximately this perturbation. And we assume that the perturbation has always norm 1. So this means that the norm of this of the difference between consecutive iterates has norm approximately 1 or more and more close to 1. So this means it cannot converge because the norm of consecutive sequence elements, if a sequence converges, must be 0. So it difference between consecutive vectors of a sequence that converges, and in particular would converge to the optimum, would need to have norm 0. But this contradicts the fact, due to the perturbation, that the norm is more and more equal to 1 because of the perturbation. So there cannot exist a sequence of weight vectors that converges to the optimum for any arbitrary choice of step sizes that satisfy this constraint. So they are between 0 and 1. Okay. So the answer was no, it's not possible to find a sequence of step sizes such that the perturbed gradient descent steps converge to the optimum of the function. But there might be certain choices for these perturbations or certain sequences of perturbation vectors that have norm 1, where the perturbed gradient descent steps or iterates still converge, but not to the optimum. So they might converge to some other point that give a gradient that just counteracts then the perturbation that you add in the gradient descent step. However, it cannot converge to the optimum. So this was the question asked specifically, can this perturbed gradient descent steps converge to the optimum of the function? So it's not asking can they converge at all, but do they converge, and do they converge to the optimum of the function? Okay. So this was a bit more tricky question, I admit. Yeah, so if we constrain the learning rate to be between 0 and 1, then the perturbation must decrease. So the norm of the perturbation must get smaller and smaller. Yes, only then it can converge to the optimum. And yeah, by the way, so what could be a source of this perturbation? Let's discuss this a bit more. What could be the source of the perturbation? Where do we have it? Let's remove this here. So we have here perturbed gradient descent. What can be a potential source of this perturbation? Is it just me as a professor, as a teacher, who wants to make a gradient descent more interesting? So just for fun, I add a perturbation term. Why could this be a useful model in practice? What could this perturbation term represent? Any ideas? Yeah, calculation errors. For example, what I write down here easily and without any effort here, this matrix. So if this is a quadratic function, then it's a matrix vector multiplication. But here it would be vector additions. But these additions, adding these vectors, must be done with finite bit widths. So with finite word lengths in a computer. So you will have numerical errors. So these perturbations can represent the numerical errors that arise because you only use 16 bits, or I don't know, 64 bits if you have a very powerful computer to represent numbers in a multiply and accumulate unit, as they are called in digital signal processors, for example. Okay, what other source could there be for perturbations in the gradient step that we actually intentionally incur? So what variant of gradient descent did we talk about in the lecture about gradient methods? Yes, so we could also say we understand well how gradient descent works for a convex function. So we know well how it works for a convex function. So it would be nice. What could we do? And in practice, you might have non-convex functions, something like this. In practice might be f this. So you could say I approximate my non-convex function by some approximation of a nice smooth convex function, and then you could say the gradient that you compute, or the gradient that you compute of the non-convex function, is actually the gradient of the convex function plus some error term. So you can then still use the analysis of gradient descent for convex functions. So this is a pretty neat use of perturbation, of perturbed gradient descent, in order to make your analysis easier of a more difficult function. You just approximate it by a convex function, and you say the gradients that you get from, actually what you compute are the gradients of this non-convex function, but you say these are close or approximations to the gradient of the convex function plus some error term. And this discrepancy here, this discrepancy is exactly what you can accommodate in the perturbation here. Okay, and do you have another idea where this perturbation could come from? What other variants of gradient descent did we talk about in the, or did I mention in the gradient methods lecture? So we had plain gradient descent, then we had, yes, so any form of hard or software failures when you have to communicate data points in order to compute the loss functions and gradients. This can give rise to these perturbations. But can you think of a stochastic source of these perturbations? So some form of random experiment that gives rise to a perturbation. So this would then become a random variable. Did we talk about stochastic flavors of gradient descent? Or do you know a stochastic variant of gradient descent? Yeah, yes, stochastic gradient descent, exactly. Stochastic gradient descent. And the idea is, instead of computing the gradient, which could be for linear regression, the gradient looks like this. It looks like a sum over all data points in your training set, and the training set might be billions, 10 to the, or yeah, billions, 10 to the power of 9. So we don't want to compute the sum, but instead, so in this sum we have something like feature vector of the ith data point, label of the ith data point minus feature transposed weight vector, something like this. So the gradient is a sum of many components, and we approximate it by using a subset or a batch of a small number of components and only sum over those. And this here is this I called, I think, a gradient approximation, and this is stochastic, a stochastic gradient approximation. And when you use such a stochastic gradient approximation, you essentially introduce an error term. So stochastic gradient descent is actually an instance of perturbed gradient descent. However, what is different in stochastic gradient descent, you can read this up in the lecture notes in more detail, you scale the perturbation term by the step size. So in stochastic gradient descent, we have control over the magnitude of the perturbation, and it's scaled using the step size itself. So in stochastic gradient descent, we can make the perturbation as small as we want by choosing the step size as small as we want. So the smallest possible step size would be alpha k equals 0. Is this a good choice for the step size in stochastic gradient descent? I mean, we would remove the perturbations. No, but what is the drawback of using this small step size, 0? What is the progress that we do in an iteration? 0, because we don't move at all, no progress. So it's not useful. So we must use step size larger than 0. And typically we use step sizes that scale with the iteration like 1 over k. Okay, so that was a little impromptu on gradient methods, gradient descent, and perturbed gradient descent, and stochastic gradient descent. Are there still questions you would like to ask now?